Hi, everyone. My name is Priya, and I'm currently a second-year PhD student at Stanford. And today I'm going to be presenting our work, which is on learning manipulation policies for robot-assisted feeding, and in particular, learning skewering strategies from multimodal perception. So robot-assisted feeding has the potential to improve quality of life for millions of people, and this includes those with upper mobility impairments who lack the ability to feed themselves, as well as a substantial portion of hospitalized elderly, nursing home, and stroke patients, as well as the caregivers who look after them. And more broadly, anyone impacted by the substantial time and effort required in meal preparation and feeding, such as families with young children and elderly. There are a number of solutions on the market for automating meal assistance, but one drawback is that they often require the user to perform some degree of manual teleoperation when it comes to performing the low-level movements of picking up food items. And another limitation is that they require an operator to have pre-programmed trajectories for transfer to a user's mouth. So this leaves a great potential for automation, both in the space of bite acquisition. And you might have seen my lab mate Jen's work earlier at CoRL on learning bimanual scooping policies. And a number of labs have also looked into automating skewering, which we build upon. And the downstream goal of bite acquisition is eventually to do bite transfer, which is transferring a bite to a user's mouth in a way that's both comfortable and efficient. The focus of this work will largely be on improving skewering strategies, as this still poses a number of challenges to robots today. So you might be wondering, well, what makes skewering difficult? Well, this is a very challenging task, not just for robots, but even for humans, as you can see here in this video of a baby trying to pick up mango slices with a fork. And more concretely, the first main challenge is that food comes in many different shapes, sizes, and scales, and we want our policy to be able to generalize across food geometries, because any slight misalignments of the fork tines with respect to the item posed can lead to slip failures, as you saw there. And we also want to avoid taking unnecessary attempts. So we want our policy to incorporate tool reactivity. And as humans, something we do is when we play with our food, we can gauge important properties, like, for example, how ripe a mango slice is. But downstream skewering, given this information, is still very challenging. And lastly, food is a highly deformable object, and we want our policy to take care when actually skewering so as to avoid the kind of smushing which you saw there. So in summary, the main challenges we're trying to address are coming up with a policy that generalizes across foods of different geometries, is also tool reactive, and is sensitive to the range of deformation behaviors that food can exhibit. Our key insight is that this task requires both joint visual and haptic sensing to enable reactive and zero-shot skewering. And we achieve this with a novel probe then skewer approach, in which the multimodal feedback that we obtain upon just making contact with food items can inform the rest of the skewering trajectory on the fly. So in this talk, I'm first going to formalize the skewering problem and then discuss our proposed approach, which we call haptic visual net, and finally demonstrate our system's performance on clearing various plates of food. We seek to learn a zero-shot skewering policy, enabling a robot with a fork-equipped end effector to be able to clear a plate of bite-sized food items. For action space, we modulate the fork pitch for sensitivity to item deformation, as well as the fork roll for sensitivity to the item geometry. And then within this action space, we can define a skewering action such that the fork starts at position XYZ, skewers downward an amount delta Z, while optionally tilting this amount delta beta. And we'll see how we use this action space to instantiate skewering primitives later on. So given this action space, what we do is we first probe food items, and given the post-contact image observations and haptic readings recorded over the first few milliseconds of contact, we want to learn a skewering policy pi, which can output a skewering action, as you can see here. So next, I'll be discussing how we actually learn such a policy with our approach, which is called haptic visual net. Before going into the full method, I'm first just going to introduce the skewering primitives, which we consider. So on the left, what you see is the vertical skewering primitive, where the fork just simply stabs an item in a straight and vertical motion. And this is intended for very hard items like a broccoli stem, for example. And we also use a angled skewering primitive where the fork actually gradually tilts while inserting into an item. And this is to support soft and delicate things like a banana slice while lifting to avoid any kind of slip. With the multimodal feedback that we obtain upon probing, this serves as input to our haptic visual net, which aims to learn a multimodal food item representation encoding which skewering strategy is appropriate for the given food item. We first encode the force features separately using an LSTM, and the image observations using a visual encoder. And finally, the concatenated cross-modality embeddings that we obtain from both vision and haptics serve as input to a final layer which just classifies which primitive to execute. Either angled skewering in the case of soft food items like the banana slice, as you can see on the upper right, or vertical skewering for hard items like broccoli. To actually train our network, what we do is we collect a set of hard food items, so things like zucchini, carrots, broccoli, and frozen foods, as well as soft food items like banana slices, kiwi, and cheese. And we simply just probe them without actually skewering to obtain paired images and force readings. And we map all of the hard items to the vertical skewering strategy and softer items to angled skewering to get action labels for free. With various augmentations, we can inflate just 300 probing interactions to a larger data set of 3,000 examples with which we train haptic visual net. After training, our full byte acquisition pipeline starts by localizing food items on a plate with bounding box detection, estimating the food item pose, and using visual servoing to bring the fork in contact with the food item. And finally, we can do probing and then skewering via haptic visual net. Now let's take a look at how our system performs on clearing various plates of food. In our system, we compare against baselines that either do not reactively plan, meaning that they do not probe, as well as two variants of our approach, which either ignore the visual or the haptic modality, in contrast to our approach, which uses reactivity and both modalities. We evaluate with a Franca robot equipped with a custom end effector mount consisting of a camera, a force torque sensor, and also a fork. And while we evaluate on both seen and unseen plates of varying levels of acquisition difficulty, let's first take a look at this plate of fruits and vegetables. So on the left is a video of a baseline called SpaNet, which is from prior work. And this is a visual only baseline, which does not use probing. And as you can see, it tends to favor these vertical strategies overall. And while that's appropriate for the broccoli, it quickly leads to these consecutive failures on banana slices as it's not able to adapt via probing. And in contrast, our approach is able to clear this plate much more efficiently by applying the vertical skewering strategy for the hard items like zucchini, broccoli, celery, carrots, and grapes. Whereas for the softer items like banana slices, it's able to sense that the angled skewering strategy is favorable after probing, which leads to much higher success rates. This is a tricky plate because it's actually butternut squash with various degrees of cookedness, ranging from raw to half-boiled to fully boiled. So on the left is a video of a visual-only baseline with no access to haptic info. And you can see that it's easily fooled by the different types of butternut squash because they are visually similar but texturally dissimilar. Whereas our approach, by exploiting both vision and haptics, is able to infer that for the raw butternut squash, as you see here, vertical skewering is appropriate, and with the more boiled variations, the angled skewering approach is appropriate and leads to far less drops and breakage. We also consider a plate of only broccoli, and on the left is a haptic-only baseline with no visual information. And broccoli is a highly anomalous food item because just by touching it, this incurs low haptic readings. So a haptic only baseline can easily be tricked into thinking that angled skewering is favorable. Whereas with our approach, it's able to use both visual and haptic sensing to recognize that this is a very fibrous food item requiring the vertical skewering strategy. So across many different plates, we see that our method in orange is able to achieve much higher empirical success compared to these baselines. But we acknowledge that this is a very challenging task. And so some of the failures that we do see in our approach are dropping, especially with adversarial food item properties like thinness or fragility, as you see with the dumpling, unstable skewers where the item is picked up but just very tenuously held on the fork, and occasionally damage or using the wrong primitive. But despite these failures, we see that with haptic visual net, we're able to reduce the occurrence and also the severity of a lot of these failure modes. So in summary, we present this system for zero-shot byte acquisition, which employs a learned policy for reactive and multimodal skewering. And in the future, we're really excited about extending to much longer horizon and more dexterous acquisition strategies, such as being able to pick up noodles, and hopefully being able to combine a system for both acquisition and transfer in one. So with that, thank you so much for your attention. I'm really happy to take any questions now.
Yes, here we go.
Thank you. So great talk. I really like the probing step as like a form of system ID. That's really cool. And I also really like your principled evaluation procedure. Am I correct that there's only two primitives for skewering, right? But at the beginning of your talk, you mentioned like 2 dimensions of motion, which are important for skewering. So can you tell us like why not use a continuous action space of these 2 dimensions? Or maybe alternatively, you know, why would that not be helpful?
Yeah, so that's a great question. You're right that in this work, we're only considering the 2 parametrized primitives. So for one of the angles, which is the fork roll, that is actually continuously parametrized. And what we do is we use the food item pose estimate that we have to parameterize that angle. For the 2 primitives, we do have a fixed tilt for vertical versus angled. And the main reason for that is that we were worried that with too large an action space, we wouldn't be able to learn a good enough policy. And a lot of prior work has actually done a lot of work in just dimensionality reduction for the primitives, which is why we went down that route. But yeah, in the future, I think it would be cool to extend to a much more like expressive action space.
Cool. Thank you very much.
Quick question for you, Priya. Thank you. Great talk. And so I'm curious about the orientation and maybe planning aspect. So do you control the orientation of the fork around the vertical plane? And then how do you choose which objects to go in which order?
Yeah, so right now we're not factoring in the order too much. We just use a out-of-the-box bounding box detector and go to any of them. And for that, we're just using positional control plus the depth image to figure out at what height to probe and then skewer. And then we always, the fork orientation with respect to the end effector is fixed. So we just send end effector orientations to orient the fork.
Hey, I was wondering what you think you would need to change if you no longer have the food directly on the plate, but on top of salad or noodles or whatever.
Yeah, that's a great question. So I do think the actual skewering action will be a lot more difficult, especially when dealing with cluttered plates, for example. We're considering adding some more primitives to our library to deal with, for example, using the plate wall as a support when skewering, or toppling an item into a stable pose before skewering. So definitely expanding our library of primitives is something we'd want to consider.
All right, thank you very much.
So for our next presentation, we have Justin Kerr presenting EvoNerf, Evolving Nerf for Sequential Robot Grasping.
All right. Hello, everyone. My name is Justin from UC Berkeley's Autolab, and I'm excited to present Evolving NERF for grasping transparent objects. And without further ado, I'll introduce you to my sink in a state that I think all of us are too familiar with. And I'm sure as roboticists, we've all thought at some point, wouldn't it be great if a robot could unload this for us? And this turns out to be quite a challenging problem because of the existence of transparent and reflective objects in sinks like these. But this isn't just to serve my laziness. If robots could grasp and perceive transparent objects, they could carry out a large scale of useful tasks in pharmaceutical, household, and industrial environments. And so the crux of the problem is that grasp planers need to use some form of geometry information, such as depth, but depth fails to sense transparent objects because of the reflections. So one promising line of work is to use learned depth completion. And so what this does is it trains a convolutional neural network on a lot of photorealistic simulated scenes to fill in the missing depth information. And this is a good strategy and it works well. However, it's very data hungry. And so it tends to struggle with out of distribution backgrounds or objects, and it has some undesirable properties like filling in cavities. And so can we avoid simulating realistic appearance entirely with something else? So I'm sure you've all heard of neural radiance fields. And maybe the scene on the right looks familiar to you from Friday night. They're a representation which can reconstruct scenes by learning a density representation, which is what stuff is in the scene, and then the color of what that stuff looks like given different directions. And the key here is that because density is a continuous value, it very naturally represents transparency because it can just put a little bit of density on the surface of a transparent object. And so you can get quite impressive reconstructions of complicated transparent scenes like my sink here or this dishwasher. So in our prior work, we found that raw depth outputs from NERF could produce viable grasps using off-the-shelf planners like DexNet. However, this was far from practical because the data sets were hand collected and training NERF took on the order of hours. So in this work, the goal is to really make this practical and carry out sequential grasping. So given a cluttered scene of transparent objects, we want to grasp and remove them as quickly and safely as possible. And to do this, we have a bimanual Yumi robot with a camera on the left hand and a pair of parallel jaw grippers on the right. And here's an example of the countertop environment that we're using. So in the past year since NERF came out, there's been a flurry of research activity speeding it up with new positional encodings, from learnable hash grids to sparse matrix decompositions to dense voxel representations. And this really enables rapid usage of NERF in robotics. And so we build upon instant NGP here. So in the traditional NERF setting, you have a data set of images, you compute your SFM or SLAM algorithm to gather poses, and then you train NERF to convergence and render the scene like Yoshi doing his CoRL overleaf paper. The problem with this is that it's incompatible with robot usage because the image set is fixed per scene, and typically training NERF is quite slow. Even with these speedups, it can take on the order of a minute. And so here we need to make NERF into an online setting. And to do this, we capture images while moving, and instead of training on a fixed data set, we train on a continuous stream of images while the arm moves. And so if you do this naively, and you just take instant NGP and train it, this is the kind of results that you get after a few seconds of training. And you'll notice that the geometry doesn't look that good. There's a lot of roughness on the outside of objects, and there's floaters, which is what the community calls these spurious locations of density floating around. So why is there such low quality? Well, NERF focuses on appearance over smooth geometry. So without incentives to reconstruct smooth geometry, it's perfectly happy to put floaters to explain what the images look like. In addition, we train on the order of seconds rather than minutes, and we have fewer views with pose error and motion blur because of the moving camera. So in EvoNERF, we introduced two geometry regularizations to encourage smooth geometry. The first takes inspiration from mesh Laplacians in graphics and introduces a 3D density Laplacian penalty during training. The second is to more coarsely sample rays during volumetric rendering, and both of these together encourage a low frequency representation of geometry in the scene. And so here's sort of a before and after of instant NGP on the top and EvoNERF on the bottom, and you can see that it much more quickly acquires smooth and graspable geometry. To get some numbers on this, quantitatively, we found that it results in about a 30% drop in the amount of capture time needed to grasp. The second part of EvoNERF comes from evolving. So instead of grasping and then throwing away the weights and then retraining on new images, this seems a little silly given that not much of the scene has changed between grasps. So instead of this, we instead throw away the old data, but keep the weights of the network, recapture a much smaller trajectory to remove the object and carry on. And so here you can see some iterative updates to the same nerf after grasps. So even with all this geometry regularization, there is still a depth distribution shift from nerf geometry to depth that you'd expect from a sensor. And this can be seen in fatter objects or wispy floaters inside. And so to handle this, we train a radiance adjusted grasp network, which we call RagNet because, well, it cleans countertops. And so to do this, our network architecture has a translation prediction head and a rotation prediction head, which takes in the cropped argmax of the translation. We train it on a variety of simulated scenes of household objects, which we obtain by throwing them into a table, sampling grasps, and then evaluating those grasps. We render their appearance in Blender, notably using random colored backgrounds, so not realistic at all. And then we pair this depth with those sampled grasps. And so here you can see the objects that we use in the top right, the training objects in Blender. And then on the left, some objects we consider within the training distribution, and on the right, outside this training distribution. And so these are the objects we use during physical tests. So the first experiment we want to ask is how quickly can we grasp one object? So really pushing the limits of speed here. And so to do this, we iteratively query the grasp confidence, and we early terminate the capture when the confidence crosses a threshold. We test on 9 objects with 3 trials each, an example of which is shown here, and find that on average, we can grasp within 10 seconds. We compare against DexNet to highlight the importance of training on nerf rendered depth. And we see that DexNet suffers with the barely converged nerf geometry, while RagNet has around a 90% success rate. The second experiment is how reliably can we clear an entire countertop? So here on the left, you can see the system progressively capturing the scene, removing an object, and then updating or evolving the nerf weights. Here is some examples of the 6 test scenes that we used. And overall, DexNet can clear around 50% of objects, while RagNet can clear about 72%. We also tried discarding the nerf weights and updating the nerf weights, and found that it doesn't result in much change in performance, while resulting in around a 60% improvement in speed. This paper has no dirty laundry, and that's because we have dirty dishes instead. So some notable weaknesses is that because of the fattened objects, sometimes grasp can miss, or it struggles with very fine details on objects. In addition, even though it's really good at removing geometry, it suffers at adding or moving objects in the scene. And of course, it's not industrial speed, but more on a household scale on the order of tens of seconds. There's some interesting future directions. For example, pre-training nerf in a sort of meta-learning sense to get more robustness to changing scenes, using the 3D geometry more holistically for 6-off grasping, using the nerf gradients to get motion plan trajectories for the gripper, as well as embedding 3D semantics. So to sum up, we present a practical nerf grasping pipeline for transparent objects that uses nerf as an updatable scene representation. Thanks for your attention, and happy to talk to you at my poster and accept any questions.
Hey, Justin, thank you for the great talk. So one question I had was, we see that kind of rainbow colored tablecloth there. So I wonder what you think in future, or is there like a reliance on that, or could you do like a monochrome one or something? And if not, what kind of directions in future work would you take?
Thank you. That's an interesting question. So we did actually qualitatively find that having colorful backgrounds actually improved some of the geometry speed. So I think it doesn't have much of an effect. So we tested with a variety of backgrounds. So I think you could expect it to work on any countertop that you put it on. And in fact, this countertop here in this GIF is just a granite countertop in our Airbnb, and you can see good geometry from it as well.
Awesome. Thank you.
So a question on my side. You right now have the robot using the second arm to sort of like visualize around it. How difficult would it be to sort of incorporate it almost like, while you're moving the hand, having something on the wrist to kind of get those images?
That's a great point. So we sort of brainstormed ideas like this. And in fact, we thought about putting multiple cameras on the arm and then sweeping the entire arm to get more views. I think it's definitely a practical thing. I think the reason that we use two arms is mostly just for speed of implementation, but you definitely could have the camera mounted on the same arm as the wrist and capture continuously as you move around the scene. It's a great point.
Would you do sweeping sort of all around, or could you just kind of during the approach do it online?
Right. So the trajectory that we use is a hemisphere because it kind of gives you maximum coverage of viewing angles for NERF. And so I think to get the best quality, you need to have some sort of sweeping motion like that. Thank you.
In the back, if we can get a microphone there.
Yeah, thanks. It was a great talk. And I wanted to build on the trajectory sort of information acquisition point. I'm curious if you have thoughts on planning informative trajectories to sort of observe a scene and kind of more naturally.
Yeah, thank you. That's a great point. So there is some related work. I think at a workshop last RSS, there's some sort of information gain view sampling for training NERF. And so I think that would definitely have an improvement in performance on larger scenes where it matters more where you put the camera. You're definitely right. That's a really interesting research direction. I think in this work, we mainly kept with the static hemisphere just because we had a small tabletop scene that we had some prior on the location.
Yeah, absolutely. Thank you.
All right. I think thanks, speaker.
Thank you.
Okay, so while our next speaker sets up, I'll read the next paper. It's called RoboTube, Learning Household Manipulation from Human Videos with Simulated Twin Environments. And our presenter is Haoyu Zhang.
I'm sorry. I don't know. How to connect to this stuff. My name is Haoyu Zhang. I'm a CMU master student. Today I'm gonna talk about our recent work, RoboTube. It's a new benchmark for robot learning from human videos. So the first question is, what is imitation learning? Broadly speaking, in imitation learning, we have two agents, an expert and a robot. We can give the robot maybe demonstrations. Let's say we have VR controller to control the robot to collect expert demonstrations. And we can also provide videos. Let's say we have our iPhone on my left hand and on my right hand perform how to open the drawer. And we can also provide maybe online demonstrators. The objective of imitation learning is try to learn a policy to mimic the expert behaviors. And today we're gonna pay more attention to imitation from human videos. So the motivation here is that robot demonstration is actually very hard to collect and extend to a larger scale, even though we have many great platforms. And the big picture idea of learning from videos is that we hope that one day we can leverage the massive source online, like let's say YouTube videos. We search how to cook a steak maybe and try to teach the robot how to do imitation learning tasks. And where are we now? So actually recently very great works, let's say time contrasting network, they collect their own data set, and also concept robot leverage something data set to learn a generalizable reward function for downstream manipulation tasks. And CoRL this year, we also have like, let's say VideoDex try to use Epic Kitchen dataset to learn some useful prior knowledge for downstream manipulation tasks. Our argument here is that a standard data set, a standard benchmark platform is still a missing part in our area. That's why we take 1.5 years to build RobotTube platform. Here's some numbers of the video data set we have. We set up 5 task families and 50 tasks in total. We have 60 household objects ranging from rigid object, articulated object, and deformable objects. We asked 9 demonstrators to go to real kitchens, let's say real offices, to collect more than 5,000 video demonstrations under more than 30 real environments. And I'm gonna talk about some of the key features in RobotTube video dataset. Some other dataset may not include. So first of all, we have 2 levels of difficulty. The first one is the structure mode. Let's say we have a clean table and we can perform the task with hand and the interacting object. The second harder level is the in the wild mode. We go to real kitchen and maybe a real bedroom to collect some real manipulation tasks. And we include both RGB and depth images for every single video. We record both the third-person viewpoint and the first-person viewpoint simultaneously. And one more thing is that we not only include, let's say, successful expert demonstrations, but also some field episodes for some self-supervised learning. So let's take a look at how we construct this platform. For example, for the water pouring task, we first collect a branch of marks. Let's say here we have around 20 marks, and we use real sense camera. We build a portable and affordable recording system with one camera on your head and another fixed tribal camera for the third-person viewpoint. And we record the human videos. But if we want to benchmark and test the model learned from videos, video dataset alone is not enough. That's why we take more efforts to build the so-called digital twin environment of using 3D scanning technology, so that the model learned from RobotTube videos can be tested, benchmarked, and reproduced in our simulated twin environments. And how we build the digital twins, we use 3D scanning technology to obtain the object model of every single object shown in the video to create a digital twin in the simulation environment. And here we collect a suite of objects data set. We split them into training set and the testing set. So we hope that, for example, reward model learning from those training set can test the generalization to unseen object and unseen environment. And it's also notable that those visually realistic assets, reusable assets, can be transferred to other platforms as well. And here I'm gonna show a quick demonstration of the simulation environment we built using Unity 3D. We take special care to bridge the visual gap between the real world and the simulation world. And we want to create a very realistic and diverse environment so that the model we learned from, let's say, real world video data set can be correctly tested in our simulation benchmark. And we can quickly verify our new algorithms before moving to real experiment setting. And we also do some comprehensive experience to benchmark existing methods of self-supervised reward learning. And we also tested some of the generalization to real-world experience. So the first part is benchmarking reward learning methods. So an overview of self-supervised reward learning is that, let's say, given a branch of videos showing you how to open or close a drawer, we train a reward model. We can create neural reward function using some passive data offline pre-training. And once we have this learned reward model, we can apply reinforcement learning. Let's say we have an agent interacting with the environment. And at every time step, we have a feedback of the visual observation, let's say maybe RGB imaging. And we take this as the input of the neural reward function, and it can give you a reward. So you can use reinforcement learning, try to mimic the behavior of the expert. And here's some of the numbers of the success rate of the three different baseline of reward learning compared with the blue curve, which is the environmental reward handcrafted by human expert. And we also did some real world experience. Let's say we teleoperate the robot to collect successful videos and we record the videos as the testing data. For example, we have a Franca closure drawer, and we want to train the reward model from those training set and testing the zero-shot generalization from human domain to robot domain and see if it can bridge the morphology gap. And surprisingly, we found that if you are able to think enough diverse objects, it can zero-shot generalize from human morphology to robot morphology. And the right is the predicted reward curve using the pre-trained reward model and tested on a successful video trajectory. And we also have other experience like waterproofing and also by manual lifting tasks, and also how to open the cabinet. And also we include some deformable objects tasks like clothes folding. Okay, and some of the limitation of the version 1 robot tube is that we take special care of the visually realistic simulation because we focus on how to do visual imitation learning, but we also try to build a physically realistic simulation. But currently there's still a gap between sim to real. We want to try to pay more attention to correctly modeling the dynamics of the object in the future and close the real to sim to real loop. And the second thing is in the following work, it might be interesting how can we quickly extend the scale and the diversity, both for the video data set and the simulation environment. Thank you.
All right, thank you. Do we have any questions? Okay, we've got one all the way over there.
Hey, thanks for the talk. Yeah, so you talked about having physically realistic simulation and visually realistic. I'm curious then why you chose to go down the route of having scans of a scene. So yes, that's nice. You get like real world textures, but to get those maps, you actually have to have a bunch of priors like smoothing, and so you end up with like overly smooth and quite janky models. So I'm just curious, like, was there a point in the project where like, okay, should we try and model everything and actually get high fidelity models and try and replicate the real world that way versus, yeah, this kind of scene scanning?
Yeah, thank you. Thank you for the question. I think we try to build the, let's say, the digital twin of the object shown in the video, so that we want to create such a, let's say, a metaverse platform to validate the algorithms. Let's say I try to propose a new algorithm for reward learning, but maybe I don't have a real robot setup. I want to quickly test if our algorithms can be validated on such realistic simulation. That's one.
Sorry, I was just saying, I guess my argument is that they don't look realistic, right? When you do 3D scans.
Yeah. I mean, we try our best to bridge the visual realistic, both from the, let's say, the objects, the appearance, the texture, and that's the first step. We want to verify if those reward functions can be work from training from, let's say, human videos and testing on those robotic experiments.
Okay, we have another question up here.
Yeah, so I just wanted to draw attention to the fact that this is an area which is being worked on quite substantially in computer vision. and the computer vision community has a lot of experience in collecting very big data sets. So a very relevant data set here, for example, is Ego 4D, 100 Days of Hands, Epic Kitchens, and so on. So my suggestion here is for all robotics people who are in this business, really look out for all the stuff that has been done in computer vision, where very large data sets with a very large amount of variety have been collected, and there's no point doing, we should work together.
Thank you, Jitendra.
Is there any way in which your data set is different from those that?
Yeah. I think Ego 40 is actually a very massive scale data set, and it mainly investigate how can we conduct pre-training and generalization for downstream tasks. But here, I think RobotTube focus on some maybe smaller scale, but we focus on task-to-task imitation learning. And I think Ego 40 is great, and we also want to try to extend RobotTube to a larger scale, maybe in the future, but I guess it's quite hard. Yes, thank you.
Okay. All right, I'm not seeing any more questions, so let's thank our speaker again.
Thank you.
Okay, the next presentation will be done online. The title is Learning to Grasp the Ungraspable with Emergent Extrinsic Dexterity. And the presenter will be Wenjiao Zhou. So tech people, please somehow make that happen. So I don't know if you can hear me, but we're ready for you to start. You're muted. Still muted. There we go.
Hello?
Yes, we hear you.
Okay. Okay. Hi, everyone. I'm Wenxuan from Carnegie Mellon University. I'm going to talk about our work on learning to grasp the ungraspable with emergent extrinsic dexterity. Consider that we want to grasp a large cereal box from the side or to grasp the tools in a certain way. How can we reach those grasp poses? In some cases, we may directly approach the grasp poses in free space, which assumes the object is static. In other cases, the desired grasp might be occluded by the table and cannot be reached without moving the object. And we call this the occluded grasping task, which will be the focus of this work. To reach those occluded grasps, it requires complex interactions with the objects. For example, we might use two hands or exploiting in-hand manipulation with our high degree of freedom fingers. If we ask a robot to perform this task, does it require a human-like hand? Although multi-finger dexterous hands have high degree of freedom similar to human hands, they're expensive and fragile. In contrast, simple grippers are cheaper, less fragile, and most widely used. Previous work has proposed the concept of extrinsic dexterity, which is to solve complex tasks with a simple gripper by utilizing the external environment. This is different from a common practice of considering the robot and the object in isolation. It focuses on a holistic view of the interactions among the object, the robot, and the external environment. And in our work, we want to use this idea to solve the occluded grasping task with a simple gripper. Previous work on similar tasks usually rely on handcrafted primitives, assumptions on contacts, special gripper design, or multiple arms. And in this work, we want to demonstrate emergent extrinsic dexterity behavior with reinforcement learning without these limitations. We will introduce the proposed system for occluded grasping from three aspects: RL problem design, dealing with a set of grasp poses, and enabling zero-shot sim-to-real transfer. We build a simulation environment for this task. For each episode, a target grasp pose is given, which is partially occluded by the table. And during the episode, the policy aims to learn to reach the target grasp pose by interacting with the object. And placing the object inside the bin can enable the possibility of using extrinsic dexterity. Although our objective is mainly about reaching the pose of the given target grasp, we can optionally evaluate the full grasping performance by closing the gripper and trying to lift the object at the end of the episode. We propose a reward function that exposes the occluded grasp while approaching it. It only has two terms. The first term is about grasp alignment, which calculates the pose difference between the target grasp and the current end effector pose. And then the second term is the occluded penalty, which penalizes the occluded portion of the target gripper. This is calculated by setting several marker points on the target gripper and check if these marker points are in collision with the table. And note that our reward function does not have any handcrafted separation of pre-grasp and grasping stages, and we do not have any term for extrinsic dexterity. So the action space of the task is end effector delta movement, and the observation space includes target grasp pose, the end effector pose, and the object pose. And for the real robot experiments, we're using ICP to estimate the pose of the object. For our algorithm, we use soft actor critic. And since the target grasp pose can be considered as a goal, we can formulate our problem as a goal condition reinforcement learning and use hindsight experience replay to, in addition to soft actor critic. And in some cases, we might have more than one feasible grasp for an object. So we also consider how to train and test with a set of grasps. During training, we introduce multi-grasp curriculum, which gradually expand the range of grasp poses. And then during test time, since we are using an off-policy algorithm, the agent can choose the best grasp that leads to the highest Q value. To enable zero-shot sim-to-real transfer, we use automatic domain randomization, which gradually increases the range of domain randomization based on the current performance of the policy. We consider physical parameters of the gripper, the object, and also the bin. Now let's look at some experimental results. We observed that the learn policy solves the task with emergent extrinsic dexterity behavior using two strategies. In the first strategy, the robot will first try to push the object closer to the wall. And then it will use the left finger to rotate the object by pushing it against the wall. And this stage usually involves a lot of contact events. And then the robot will let the object drop on the right finger in order to reach the target grasp. And at the end of the episode, we command the robot to close the gripper and try to lift the object to measure the success. And interestingly, in some other cases, the policy shows a second emergent strategy. It will try to rotate the object until it stands on the side, and then the gripper can try to move close to the target grasp. We also found that the policy demonstrates recovery behavior. For example, when the object drops unexpectedly, the policy will try to rotate it again. And in this example, when the object bumps on the right finger, the policy switches from the dropping strategy to the standing strategy. We evaluate the policy across objects with various surface friction, density, and shapes. And most of the objects are out of the distribution. And although the policy is only trained in simulation with box-shaped objects, it is able to generalize to different shapes to some extent, as long as the object pose distribution remains similar. Quantitatively, the policy can generalize across different objects with a 78% success rate when trained with ADR and 45% higher than without ADR. And in simulation, we show different design choices are important for this task. For example, without the wall, the policy cannot find a way to solve this task. And without the occlusion penalty, the policy often gets stuck at a local optima of trying to get close to the grasp without moving the objects. When dealing with a set of grasps, the policy trained with curriculum shows significantly different behavior for different ranges of grasps. For example, when the curriculum starts from a grasp pose from the side, the robot may use another side of the wall to reach the grasp. For more quantitative results on baselines and ablation studies, please check out our paper. Now let's discuss the dirty laundry list of our work. First, to get emergent extrinsic dexterity, the wall needs to be reasonably close to the object. Otherwise, the policy might have trouble exploring the strategy of using the wall. Second, our policy is only trained with box-shaped objects with object poses without any shape information. And the assumption we made over here is that the non-box test objects have similar dynamics as box-shaped objects. In order to improve the generalization across more shapes, we may consider training with more shapes in simulation or use a better representation of shapes such as point clouds or key points. The third point is that sim-to-real is challenging. We include all the details for sim-to-real in the appendix. However, there's still a lot of room for improvement. In the future, we may consider more extensive domain randomization, system identification for robot parameters, or fine-tuning with real-world data. For more discussion and videos on the failure cases, please check out our websites. In summary, we present a system for the clearly grasping task that shows emergent extrinsic dexterity with a simple gripper. It demonstrates contact-rich and dynamic behavior on a real robot that can generalize across various objects. Here are the takeaways of this work. First, simple grippers are underrated when combined with a skillful policy. Second, robots should exploit extrinsic dexterity for more skillful manipulation. And lastly, reinforcement learning can generate policies with emergent extrinsic dexterity that transfers to the real robots. And when these aspects are combined, we can unlock the potential of manipulation. Please check out our paper and the website for more details. I'm also happy to chat more at the following poster session. Thanks for listening.
Thank you very much. Very interesting talk. So do we have any questions from the audience? Over here.
Thanks. Great talk and really fun to see robots manipulating things in clever ways. I'm curious about how you imagine extending this to a more general set of extrinsic dexterity strategies. In particular, the reward function you use seems to introduce some bias that's particular to this class of strategies. And I'm wondering if you have thoughts on, if you wanted to be much more general, what path you might take to get there to see a broader, more diverse set of extrinsic manipulation strategies.
Yeah, thank you for the question. I think our reward function is mostly designed for this task of grasping the object, but actually there's no reward term on extrinsic dexterity. So I think to extend, if we want to see more of these kind of extrinsic dexterity behaviors for other tasks, then the first thing to do is just to put the objects in bins so that it has the possibility of using the external environments to do more clever behavior. So I would say that it is more about the design of the environment that induces extrinsic dexterity than the reward function we actually use.
Thank you.
Other questions? Okay, I had a question actually about some extensions of this that might be possible. So it seems to me that a lot of robots today are multi-arm, what would it be like to use the other arm as the wall? And could we somehow search over policies for doing that?
Yeah, I think that's a very interesting point. And we've also considered this during the early stage of the project. And I guess we should, in the future, we should be able to let the agent learn to use any kind of help from the external environment. So for example, if there is a wall, it can try to use the wall. And if there is no wall, then it can try to use the other hand to serve as a wall to finish its task. So I guess it's about reasoning about different types of help from the environment and reasoning about having the other arm as the additional help for the task.
Great, thank you. Okay, is the next presenter here? And okay, please come and set up. Okay, let's thank our speaker again. Okay, and the final presentation of this session is called Instruction-Driven History-Aware Policies for Robotic Manipulations. And our presenter is Pierre-Louis Guhou.
Ivan Laptev.
What's that? Oh, I'm sorry. It's actually Ivan Laptev.
Excuse me, which one? Which cable is it? Is it okay. Right. So thanks for staying for the last talk of this conference. I'm Ivan Laptev. I'm from INRE Paris. I'm going to present this work, which was mostly done by my student, Pierre-Louis Gour, who could not join the conference.
Hi, Darabad.
There are plenty of tasks which we would like to offload to robots in home environments, starting from furniture assembling, cooking, dishwasher, upload and cleaning, wardrobe, arranging the clothes. And this is, if this is not enough, then you've seen also this conference, there is a new benchmark behavior 1K, which has lots of interesting tasks. Right, so why are we not here? And how far are we, and why can't we just buy on Amazon these robots which will do all this for us? So let's look at challenges. So these are not, this is not a complete set of challenges, but these are few challenges which we are interested in this work. So first is there is a plenty of different tasks. Of course, we need policies for solving them, but also even just naming them. Like if we go through labels, that's unclear how we should deal with them. So then there is a fact that the current observation of the current moment do not reveal the previous states of the world and actions, like in this famous shell game. Some tasks need precision, and then the tasks are complicated because we have unstructured, complicated environment. So if you want to go through simulation of all of these, this might be very complicated. Right, so what can we do about this? So how can we address these challenges? So these are not new ideas. So first, okay, what about if we are going to address many tasks? Maybe you should go through language. So that's maybe not the end answer, but this is at least one possibility to address this. For the past observations, we have a history. So our agents have observed the actions and or performed the actions and observed the scenes. So we can just have for example, an explicit history for all observations. For precise tasks, we could have depth sensor, we could have multiple views. And to handle the complex scenes, at least at this moment, probably it's a good idea to go via policies which are learned directly from measurements without trying to explicitly understand the world. Now, so all these ideas have been around, so we are not new to, of course, to explore them. So what may be different in our work is that we try to combine all these modalities and to learn all of them from all of them together. And how we do this? So we do it with transformers. So transformers are trendy, useful. They come with an expense of being slow at training and at evaluation, at inference. So at least in vision, sometimes if you want to have really fast system, actually they may not be the first choice for you. But what transformers are really good is to combine different types of information. So so you can basically everything what you see here are tokens. So images can be tokenized, text can be tokenized. If you have multiple frames, you just have more tokens. If you have multiple views, you also have just more tokens. So everything tokens. So if you have sound, if you have tactile information, we are not using it, but this could potentially all go in here. And that's in my view, this is one of the great things with transformer, which can bring us one step further. So we are trying to exploit this. And so this is our history where instruction conditioned multi-view transformer, which we call HiFormer. And I'm going through it piece by piece to show that, okay, transformer is transformer, but there are still important design choices that should be made. So one is language. So how do we encode language? We are not trying to do something special, but at least it's a good choice here is not to take some pre-trained language model, which is just BERT, which is trained pure language. So we can take a CLIP. So CLIP has two parts. One is a language model, one is a vision model, because they're trained together. So CLIP as a language model here is better because it's visually grounded. All right. Okay. So how do we take how we combine multiple views and the history? So we just take all observations from the past and multiple views. And now, what is actually how do we process our images? Okay. So we have RGBD input, and we also encode the proprioceptor information as a channel. And then, so this is passed through UNet architecture, so which gives us three-dimensional features. And now we should tokenize them. So we should somehow get tokens from each frame. So here are two possible ways, channel-wise and patch-wise, and I'll see that this choice is quite important. Another important choice is if in transformer, if you are going to use cross-attention or self-attention. So self-attention will be putting all tokens together, and the Q, V, and K would be just the same vector. So here Q is, in our case, our observations of the current time, and we are contextualizing them with the frames and language input from previous frames, right? So we are using cross-attention. And at the end, once out of transformer, we get features which are then back formed into grids, which form kind of images or heat maps, and we are training this with behavior cloning, which will predict the position of the gripper in the next frame or in the next step. Right, I hope this is clear. So then now evaluation. So we are looking at one of the bigger benchmark, which has 100 RL bench, which has 100 tasks. So it has RGBD input. So we are selecting 74 tasks which we were able to simulate. So we could not simulate all of them for some reason. So we evaluated in single task and setting and multiple task setting, means that we learn either one network per task or all networks per one network for all tasks. So interestingly here, so we have language, but language actually not needed because all the tasks are separate and it could be just modeled as a one hot vector. So we are also looking at variation of particular tasks where now language becomes important. So why is it important here? Because for the task of sequential pressing the buttons, so the text says press red, then green, then white, then green, then gray. Okay, this is in training, and in a test we want to have different sequence of colors. So obviously, if our agent does not understand language, it will not be able to perform the task. Okay, so these are scenarios which we consider. Now, so evaluation on 10 tasks, we have transformer with multiple view inputs and multiple, but yet without history, so it gives 5%. Then the history gives 3.7%. We get some boost from the right choice of this patch feature. So patch feature, actually, they give the spatial information, they're useful. And then at the end, the cross attention also quite important, gives us 4% altogether. So this sums up to about 15%. Comparison state of the art, were recent papers addressing the same task, same benchmark. So we are confidently above them, both in single setting and multitask setting. So they evaluated still on 10 tasks. So we are doing it on 74 tasks. So here we also see quite a bit of boost on average. Interestingly, it's good to look at because we are modeling multiple views, we're modeling history. So history appears to be particularly important for tasks. So we have grouped tasks together just to analyze them better. So for planning, for tools, and for long-term tasks, history is helping more. Multi-view are, as expected, helping more on precision tasks like screwing and others, or when there are occlusions. All right. So and then now to the variations. So here is where the language kicks in and is important. So here in this table we train, and we have synthetic testing but unseen. Okay, for two tasks, for push button and for tower. Tower is when we stack towers of cubes of different colors. Again, so the sequence of colors in the tower is not is different from training and from testing. So the agent has to understand language. So we see here the performance drops, not drastically. And so this test is when going from synthetic to real, we have collected language instructions from humans. So just we give them these pictures of, say, buttons which should be pressed, and they generate language. And then we put this language straight away into the agent, and it's supposed to finish task. So we also tried it on the real robot. So this is where we just take the simulator trained policy, and with a bit of fine tuning, we directly transfer it to real robot. It was done by Ricardo, who is here in the audience. And that's about it. So summary, so transformers are a good way to combine information also for robotics, especially because you have very different types of information, like proprioceptory or the haptic, which we didn't do. So our transformer for this particular task shows good results, and also shows promise to perform unseen tasks, which are suggested by language. Now limitations. So for some reason, so when we tried on 74 tasks to learn one policy, it didn't work that great. So we believe that might be because of capacity of the network. Long horizon tasks are still complicated because of the exposure bias. We still do BC, and yeah, the memory would become complicated if we because we are modeling it explicitly. And then okay, we have some drop in performance for natural language, which is written by human. I guess this could be addressed by learning the models on real human instructions. Thanks.
Okay, thank you. Maybe we have time for one quick question. If there's any quick questions, Ken?
Thank you. I'm just curious in your, do I understand the physical experiments? Can you say more about what the physical experiments that you performed are? Because I don't see this as a future work. So you consider the physical as being completed, and what did you do there?
Sorry, I didn't get it. So physical?
Physical, doing experiments in the physical world.
Real world. Yeah. Sure. So that's the task which we trained in simulation. Okay, and then
this is the task you're testing with, a single task.
That's one of the that's the variation of the task. Yes.
No further questions.
Okay, the prosecution has rested and the session is closed. So fun at the coffee break. Let's thank our speaker again.
Just a reminder that the poster session is going to be at 3:50 after the break. So please come back here for the spotlights. And we also have the award session closing at 5:05.